Okay, I'm gonna give this like a minute for people to show up. It seems like we already have a bunch of people here.
Great.
All right, let's get started. So we're going to be hearing from Matt McCormick from Kitware. He's going to share a bit about the ITK widgets tools that he's been working on with his team. So take it away, Matt.
Thank you, John. Hello, friends. I hope you're enjoying your SciPy. So as John said, today I'm excited to share with you ITK widgets. It's a Python package that integrates with the SciPy and Jupyter ecosystem and supports visualization of large images, mesh, and point set data sets in 3D and 2D. We will provide an overview of image volume rendering, slicing, and data probing capabilities, and the techniques used with these interactive 3D widgets. What's on the agenda for this presentation? First, we will discover the need ITK widgets addresses and some of its main features. Then we'll walk through a how-to for effective interactive volume rendering. And finally, we will conclude with some future directions. Our modern scientific process, open science, is founded on open access to articles, open data sets, and open source code. Our scientific Python community has generated essential open science tools that advance the frontier of our potential knowledge and understanding. Indeed, our computational environment has dramatically improved since the early days of the SciPy conference, when computational lab notebooks were not even aspirational thoughts in Fernando Perez's mind. It's difficult to imagine the profound ubiquity and rapid evolution of artificial intelligence in recent years without Python. So in this modern computing environment, where are our research components located? Massive data sets are generally located near where they're acquired due to their inertia. Compute resources can be a researcher's laptop, a laboratory workstation, a cloud computing cluster, or a high-performance computing cluster. The most important research component, the researcher, is not necessarily near these data or compute resources. In fact, they may not have direct physical access to these resources. Pandemics happen, as we know, or they may just prefer to code at the beach. And web browsers provide a bridge that connect these computing research components. So in this context, ITK widgets provides web-based 3D and 2D spatial visualizations for Python. These interactive tools allow us to explore, probe, and understand spatial data sets. The widgets integrate into the Jupyter Literate programming environment, work with large, remote data sets, and operate on standard Python data structures and interfaces from the community. What types of data are supported? We have 2D and 3D image support. These images, their pixels, can have anisotropic spacing and live in a world coordinate system. And spatial context is provided with a scale bar or a coordinate system grid. Volumes can be viewed with volume rendering or slicing. We can interactively select and probe array values and their location in the dataset. What's more, label images can be used to render segmentation results along with an intensity image in 2D or 3D. Label images use categorical color maps, and their weight relative to the intensity image can be modulated in 2D or 3D. We can also render 3D meshes and vector data such as lines. So now folks can interactively ponder how spherical is their cow, or interactively ponder how toroidal is their bunny. Point sets can also be rendered. A 3D perspective on feature distributions is very insightful when inspecting data sets for statistical analysis or machine learning. Another common application is the rendering of LiDAR and similar 3D point cloud sensor data. And we can render image, meshes, geometry, and point sets together in the same interactive 3D world coordinate system. Here are a few examples where volume rendering is combined with geometry, like segmented vessels from a brain magnetic resonance image. These spatial data sets can be directly rendered from many Python data structures. This includes NumPy arrays, NumPy array-like objects such as Dask arrays, ITK images, PyImj images, ITK meshes and spatial objects, VTK polydata, structured grids or unstructured grids, and NumPy array point sets. These widgets provide a simple, imperative interface designed for quick and easy usage in a notebook. As with other visualization libraries, there's also an object-oriented interface. The object-oriented interface exposes SciPy widget traitlets. For those who are not aware, traitlets are typed property of the widget that can be set or get. There are many SciPy widgets in the Jupyter ecosystem. Jupyter provides a standard library of traitlets for user interface components and common outputs. And there are many additional packages that provide traitlets. A function can observe an SciPy widget traitlet. Every time that trait changes, the changed widget value is passed to the function. This allows us to easily combine widgets or execute processing functions in response to user input to build custom interfaces. One of the higher order widgets available in ITK widgets is an interactive line profile widget shown here. We can interactively select the endpoints of a line. When an endpoint changes, a line profile is generated and plotted with another plotting library, providing traitlets such as matplotlib or plotly. Here's an example of how widgets can be combined. We provide a visualization of the common coordinate framework, an atlas that neuroscientists use to reference structures in the mouse brain. These structures are organized into the hierarchy. We can use IPyTree to interact with the hierarchy. Tools like Voila can be used to readily create bespoke applications for research data and processing. It's worth noting that even though we're using a web browser, the user can interact with their data in 3D and in real time. And we can support large data sets. In this example, we're interacting with a 2500 by 2500 by 1000 voxel volume on the NERSC Jupyter Lab cluster at Lawrence Berkeley National Laboratory in California. However, we are interfacing with the data in North Carolina, over 2,000 miles away. When visualizing these data sets, a multi-scale representation is generated, and the current scale is indicated along with the global scale with a scale bar. Color maps can be selected interactively or programmatically. We can use the color map shipped with the package or matplotlib color maps, or color maps in the matplotlib format from the color set or paletable packages. You can even specify a color map of your own with a 3x(n) NumPy array. You can use your favorite Viridis color map or channel your chaotic energy by putting np.random to work. Speaking of color maps, let's think about how we understand color maps for effective 2D image rendering. Then we'll step it up a notch and learn how we can interactively generate effective parameters for 3D volume rendering. The scientific data sets that we have are often scalar intensities, and a color map specifies a function that maps intensities to colors. The pattern of colors impacts our perception of the image data. And image rendering is highly influenced by the statistics of the underlying pixel intensities. ITK widgets provides a histogram of the pixel data being rendered and an overlay of the corresponding color map values so we can understand and optimize this relationship. Here we see the varying intensities of this tooth, computed tomography images, background pixels, dentin, and enamel, and how they relate to the map colors. In addition to the pattern of colors in the color transfer function, another critical set of parameters for color mapping are the minimum and maximum intensity values of the input used for the mapping. Contrast in the rendered image is determined by the minimum and maximum intensity values. Again, the histogram is extremely useful to select these values. We can interactively change these values, input them manually, and quickly find the range of intensities of interest in our data. Now for volume rendering. What are the parameters for volume rendering and how do we select them? In itkwidgets, we use the same color map for rendering image slices and for the volume rendering. We can observe a conceptually consistent relationship between the slicing planes and the volume rendering. As with the color transfer function, we also share the minimum value mapped and the maximum value mapped for volume rendering. In volume rendering, the minimum value and values below will be fully transparent. The maximum value and values above will be fully opaque. But beyond the color map, volume rendering has additional crucial parameters. The first parameter we will look at is the gradient opacity. We can modulate the local opacity by the magnitude of the gradient. The gradient opacity can be used to highlight structures defined by edges. It can also be a critical feature to ignore high-frequency noise. In addition to the gradient opacity, shadowing can also be enabled to enhance interpretation of edges. Another crucial component for effective volume rendering is the opacity transfer function. This function specifies the opacity associated with each intensity value. Unlike color mapping, a simple single linear transfer function is often insufficient for volume rendering of real data sets. In itkwidgets, the opacity transfer function is visualized in the curve overlaid on the histogram. High values have high intensities. We can modulate the overall opacity by changing the magnitude of this function. We can also isolate or highlight types of content that have similar intensities with this modulation function. The modulation of this opacity transfer function is parameterized by Gaussians. Multiple Gaussians can be added to highlight different intensity clusters. The package is still highly experimental, and based on the excellent feedback and suggestions from the community, experiences with the web platform ecosystem, advances in the web platform, a major refactoring is in progress that will result in significant improvements in robustness and our ability to address the community's needs. This refactoring is a collaborative effort with the ImJoy team. ImJoy is a project that we love, and it rings true to its name, bringing Pythonic level joy to the practice of imaging, spatial analysis, and deep learning. What is ImJoy? ImJoy is a plugin-powered hybrid computing platform for developing deep learning applications such as advanced image analysis tools. But what exactly is ImJoy, from all those words? Fundamentally, ImJoy is a plugin system that brings symmetrical, transparent, remote procedure calls in both Python and JavaScript. As a result, ImJoy provides powerful and extendable computational backends for browsers, local and cloud computing, supporting JavaScript, native Python, and WebPython, so WebAssembly in the client side. It has an async and await syntax. It's beautiful, which is used with Python 3 and JavaScript. And ImJoy supports ND arrays from NumPy for data exchange. ImJoy contributes to the refactoring's major capability improvements. The future will see extensive improvements to the ability to integrate, extend, and interact with the package. It was very exciting to see that the Jupyter team has dramatically improved the experience for users by removing the requirement for Node.js when installing extension packages with JupyterLab 3. As an extension, we're working through the TypeScript migration to adapt to the new Jupyter 3 extension system. We're also excited to make the widgets usable in more contexts outside of the Jupyter Notebook, including Jupyter Lite, Google Colab, TensorBoard, Visual Studio Code, Streamlit. The architecture is being decoupled, so customized front ends can be easily created. These front ends can be coupled with custom rendering backends, where rendering occurs client-side or server-side. Finally, we plan to improve the API so it provides a more intuitive plotting style interface. We will make the API as consistent as possible with other excellent projects in the community, such as Matplotlib, or Dapari, and PyVista. We want to thank the community for their feedback and contributions. Also, a few individuals have been particularly supportive, namely Danny Ushizima and Stephen Aylward, and they deserve special thanks. We'd also want to recognize funding sources. While this has not been a particularly well-funded project in the past, that's now changing, and we're excited about an uptick in the near-term progress. So in conclusion, ITK widgets can help you obtain insights into your spatial data in Jupyter's interactive environment. ITK widgets provides web-based visualization for 3D and 2D images, meshes, and point sets. Interactive tools are available for effective volume rendering, and a good way to get started is with NumPy arrays. Try out the package with pip install ITK widgets, and we encourage you to reach out on GitHub, Twitter, and email. Thank you. And I think we have time for questions if there are any. Yes?
Yeah, thanks, Matt. Yeah, there are a few questions coming in the chat, so I can just read them and you can answer if that's all right. The first one is, what volumetric data formats can you ingest? So right now, the image data structure that's used in the package is based on NumPy arrays and spatial metadata that describes the NumPy arrays. So how far away are the voxels from each other? So if you're doing microscopy or many other working with real data from 3D data sets, they usually have a different spacing in one of the directions, maybe the Z direction. So anything that can read data into that format will work. So you can use ImJoy, you can use TIFF file, you can use ITK, you can use any of the packages that work well in the ecosystem to read in your data, ZAR. So ZAR-based images, the OME ZAR will work too. Thanks, Matt. Next question. Can you handle visualizing time-dependent data with ITK widget? So that's time-dependent support will come as part of the great refactoring that we're working on right now as part of that. So for responsiveness, we do multi-scale data is one of the tricks that is done to get responsiveness for large data sets. And for time-dependent data sets, we're working on a representation of the data where we can slice in the spatial dimensions and the time dimensions so you can interactively work with data in that way. So
that's how we're adding time support, but it's not there right now. Or it's slower. It's not as interactive right now.
I'm sure users will be excited to have that feature once it's out. The next question is, does itkwidgets support server-side rendering? Or does the data in its entirety need to be communicated back to the client?
And that's a good question. So right now it communicates data from the server to the client through compression, but also it'll only communicate these beautiful data slicing capabilities we have in Python, only the data that it needs at the scale that it needs that is useful to visualize. So that's why it's as responsive as it is. But in this refactoring where we're using ImJoy, which kind of transparently, in effect, can give you code that's working either client side or server side and can switch between the two, we'll have the ability to also support server-side rendering, in which case the data is rendered on a GPU on the server, and then it's sending the rendered image frames to the client, and then mouse events and keyboard events on the client are sent to the server for rendering.
Thanks, Matt. Do we have any more questions? We have maybe a couple more minutes if people have questions that they're still wanting to ask. Okay. If not, thank you, Matt. That was a great presentation. And if people have more questions that they didn't get a chance to ask here, feel free to talk to Matt afterwards. Thank you.
Thank you. Thank you, everybody.